Hi there and welcome to this video for Senior Physics on Electrostatics and Electricity. In this video we're going to explore Kirchoff's laws. Now basically Kirchoff's laws are a set of laws which allow us to solve complex electrical circuit problems. And there are two laws which we utilize. There's the current law and then there's the voltage law. I'm going to explain each of these laws with a example for you to work through. Then check out at the back or further on in this post, there's a more complex exemplary video which runs through a more complex question for you to solve. So Kirchoff's current law basically works on the premise that when you get a junction between two different currents or two different loops of a circuit, the amount of current going in must equal the amount of current going out. Again, it comes down to this energy conservation law. So what comes in must equal what comes out. So let's take a junction like we've got in the diagram that we've got here. You can see that the arrows, we've got one arrow going into the junction, that's the white blob, and then we've got two arrows coming out of the junction. So basically, whatever goes in, I1, the current going in, then splits up and goes out I2 and I3. Now whether they split equally is all dependent on the type of resistors in those specific loops. But basically what we get is whatever I1 has coming through, when we look at I2 and I3, they will combine together to actually equal I1. And likewise, as they join up, we may have I2 and 3 joining up, and I1 will basically come out as a combination of these. As a result, for the current law, we get an algorithm of I1 equals I2 plus I3. The current coming in equals the two currents coming out added together. So let's look at a quick example. So we're going to calculate what the value is of I2 in this circuit. So all I've done is taken the junction that I showed on the previous slide. I've added values to I1 and I3, and we're going to use the algorithm to calculate I2. Now what do we know? Well, we know that I1 going in equals I2 and 3, the currents coming out. So I know what I1 is, it's 10 ohms. I know that I3 is 3 ohms, and I know that I2 is something I've got to find. So I have my algorithm, I1 equals I2 plus I3, and I can then substitute in my values. So I get 10 ohms, which is I1, equals I2 plus I3. So if I rearrange this to make I2 the subject, I get I2 equals 10 minus 3. So obviously, it's very, very simple. I2 will equal 7 ohms. Now obviously, if you've got more wires coming out, you're just going to increase the algorithm. And you might have 2 or 3 coming into the junction and maybe 2 coming out. You use the same rules. You'll just have more currents on one side of the equal sign than on the other. So you just apply the same process and you won't go wrong. Remembering the current going in must equal the current going out. Now the second one is the voltage law. And again, this works on the principle of energy conservation. Basically, it states that the energy that is put in must also be the energy that comes out as you run around the circuit. As a result, the net amount of energy will be zero. What you put in must come out. Okay, so whatever you have when we deal with voltage, we get a zero value. Now, when we deal with voltage, we can also employ the V equals IR scenario, because we don't always know V, but we know what I is, and we can work out what the resistance is, and vice versa. So we can work out the voltages, and as a result, we produce an algorithm of positive and negative values, all eventually equaling zero, depending on whether we're going putting energy in or taking energy out. So the general rules are as follows. For a voltage source, such as a battery, if the potential difference as we run around our circuit is positive, we're going negative to positive. So if we go from negative to positive, we basically give the voltage a positive value. Likewise, if we run positive to negative, we give it a negative value. Those are the laws that are applied. Now remember that when we're dealing with these circuits, we run generally using conventional current, running from positive to negative. So basically, if we're running negative to positive, we're going against the current, and as a result, we are gaining energy. And I'll talk more about that in a moment. Now, with respect to resistors, what we get is the potential difference is negative if we're going with the current. Well, negative means it's going out of the system. Okay, so if we're running with the current, so the current flows through the resistor, then energy is going to come out. And that makes sense. Likewise, if we go in the opposite direction to current, then the result is we are going to gain energy. So we work on that similar principle. Now, don't worry too much about trying to understand why this happens. Really, this is a process of just solving the problems. But let's look a little bit more as to how we get these positive and negative values. So here what I've got is a circuit, very simple circuit running through a resistor. You can see that I've got my negative and positive values on my battery, and I've got my resistor. Below that, I've got a river. Now the river works on the principle that it's flowing downhill. It's going to flow positive to negative, so we're going to be using conventional current. Positive at the top, negative at the bottom. Now, basically, what we can then state is that going uphill is like gaining energy. Going downhill is like energy coming out. So you gain energy as you walk up the hill, and then you lose the energy as you flow down the river. So think of taking like a rubber raft or something up the river. You take it up the river, you gain energy, but as you flow down the river, you lose that energy. Think about GPE, gravitational potential energy, and that sort of makes sense. You gain GPE as you go up the river, and then you lose GPE as you come down the river. So whatever you've put in to go up is what you get out as you go down it. So let's try and apply this to our circuit. Well, we can see that we're running conventionally, so we're running anti-clockwise in this case. So in the first case, we've got the battery. Now, if we follow our rules, running negative to positive means that we gain energy. It's like moving upstream. So we're gaining energy as we move upstream, so we give it a positive value. When we get to the yellow arrow on our circuit, nothing happens to the energy. So there's no energy gain or there's no energy loss. So it's zero. When we get to the resistor, we are going with the flow. So you can see there that the arrows are going with the flow. They're going in the same direction as the red arrow. As a result, because it's going with the resistor, we use that first point on the resistor rule, and the result is we're going downstream. We're going to be losing energy. Because we're losing energy, it's going the opposite direction, so we give it a negative value. And finally, our green arrow, we have no energy gain or loss as it goes back to the battery, so as a result, it would be given a 0. It's like staying in the same position. So notice as through the battery, we go negative to positive, we go upstream, we gain energy. In the resistor, we're going with the flow of current, so the result is we're losing energy. So let's look at an example. So here we're going to look at a diagram which shows part of a circuit, and we're going to calculate the EMF of the battery. So we want to know what the EMF of the battery epsilon is between point A and D. So what we do, we start off on one side and we go round in a conventional. We're going to go clockwise round. You can see the arrows going clockwise round. So we're going to start off by looking at B and C. So to go from B to C, I go negative to positive. By going negative to positive, the voltage is plus 6 volts. I gain the energy, so it's a positive. Then I go C to D. Now in C to D, I'm going through the 4 ohm resistor. Now I want to know what the voltage is going through the 4 ohm resistor. So I use my resistance law, V equals IR. Now I know I because it states going from C to D, there is 2 amps of current, and I know my resistor is 4 ohms. So I've got 2 times 4 equals 8. I'm going with the flow, so it's a negative voltage which is coming out. So remember, with the flow in a resistor, energy comes out, so I show that as a negative. I'm now going to go through the resistor in D and A. Now you'll notice in D and A I've got a resistor and then I've got a battery. So let's have a look at that. So going from D to A, let's look at the 1 ohm resistor. Now I know there's 3 amps of current going through the resistor, and it's got a resistance of 1 ohm. Now I can calculate the voltage, V equals IR, by 3 times 1. But look, as I go from D to A, I'm going against the current. By going against the current, it means that I get positive 3 amps. Okay, remember when I'm going with the current, it's negative, it comes out. So if I go against the current, I'm gaining energy, I'm going upstream. The result is I've got a positive 3 volts. Now going through the battery, notice I'm going positive to negative. So in this case, it's got a negative value. So my unknown battery has a voltage of negative epsilon, on the negative EMF. So now what I do is I put all those together and make it equal zeros. So as I put them all together, they've got to equal 0. I write down exactly what I've got. From B to C, I've got positive 6. From C to D, I've got negative 8. From D to A, I've got positive 3 and negative E. All I now have to do is rearrange it, take epsilon to the other side and solve, and I make out that epsilon has a voltage of 1 volt. Okay, well I hope that makes sense for you. Do join me again. I've got another exemplary video for you to watch. I hope you found it useful. Follow the laws and you'll be okay. And as a result, I hope you'll join me again and we can run through some more work on electricity. Thanks for watching and bye for now.